Hello, and here we are at lesson 11. Today we are going to talk about another very common model, and that is linear regression and curve fitting. So, first of all, what is linear regression? So, linear regression is a really common statistical model, and it is popularly known as fitting a line. And essentially, when we perform linear regression, we have two variables, an independent variable in which we put on the x-axis, and a dependent variable on the y-axis. And these variables, they have a correlation. Linear regression provides a linear relationship, which is a linear equation that best describes this correlation. The most common method used to perform linear regression is the least squares method, which is we minimize the sum of the square of the y distance, also known as the residual, which is basically the difference between the y value of a point and the best fit line, and we try to minimize the sum of the square of the residuals. Now, let's look at four most important assumptions of linear regression. You can remember them really easily by using line, linear independent, normally distributed residuals and equal variances. And essentially, what these four assumptions state. First, linear. You need to have an approximately linear relationship to properly use linear regression. For example, in the example on the right, you can see that the correlation between the x and y variables are close to being linear. Second, independent. It means that the data points are independent from each other and they do not influence each other. Third, normally distributed residuals. This means that the data points tend to be closer to the best fit line and is more concentrated toward the line and less concentrated away from it. Finally, equal variances. It is a really important assumption, and it is that data points are equally spread out at every x value. This basically means, for example, an example on the bottom right, you can see that for x equals to 0.2, the data points are spread out at about plus or minus 0.5 away from the line, and at a value of x equals 1.0, it is also spread out about that much away from the line. Now let's look at curve fitting. Curve fitting is really similar to linear regression, except for that the function is not linear. Because curve fitting offers so many possibilities, you need a clear reason for why you use a certain function. There are two common reasons. One reason is that it is a common function for a certain field. For example, it is a formula. Or another reason is that it is a function that you derived from the previous steps of your calculation. In curve fitting, you will have a number of parameters. Each parameter is a quantity that you can change to produce the fit. For example, a standard quadratic function would have 3 parameters. However, to make sure that your curve fitting is the most optimal, you should keep the number of parameters as low as possible. Finally, to further enhance the result of your curve fit, you may want to set bounds for your parameters whenever needed. These bounds restrict the parameters to certain values. For example, they force a certain parameter to be positive. Now let's take a look at how we analyze and present our linear regression and our curve fitting models. So for linear regression, we can use Pearson's correlation, or R, as a method of analysis. R takes on a value between -1 and 1, with -1 indicating a strong negative correlation, 0 indicating no correlation, and 1 indicating a strong positive correlation. Another way we can use to analyze both linear regression and curve fits is through the coefficient of determination, or R squared. The coefficient of determination tells us the proportion of the dependent variable that we can explain with the independent variable. For example, if we have an R squared value of 0.90, this means that 90% of the dependent variable can be explained by the fluctuation in the independent variable. Another method we can use is the chi-squared goodness of fit test. As to how we present our linear regression and our curve fitting models, we normally use a scatter plot with the fitted function clearly plotted. And for situations in which we have multiple parameters, we may want a table to demonstrate our parameter to make it easier for our audience to read. Now, let's look at how we are going to deal with more than two variables. One method is through multiple linear regression. Multiple linear regression is essentially linear regression, however, you have more than one independent variable. Another method is a surface fit. A surface fit is similar to a curve fit, however, you are fitting a three-dimensional surface, which means that you have two independent variables. Finally, as you use a surface fit, you should think about how you are going to present it, because 3D plots are not always the clearest way to show your fit. And that is what I have to share about linear regression and curve fitting. Thank you very much.